All right, now we're going to take a look at something that's called the dot product of two vectors. Here's a definition. So if vector u, if in component form it's a, b, and I wrote over here if it's in the linear combination of ij form, which would be an ai plus bj, and then vector v is cd, or that's what it is a linear combination of I and j, the standard basis unit vectors I and j, to do the dot product. So u dot v, that's how you would say it. You would say u dot v. To dot product two vectors, you just simply are taking a times c plus b times d. That's it. That's dot product. It's going to give you a number, or a scalar if you prefer. So here's a quick example. Vector u in component form is 2, -1. Vector v is 3, 4. Find the dot product, u dot v. So u dot v is just simply 2 times 3. I'll write that down. 2 times 3 plus -1 times 4. 2 times 3, 6, plus -4. So u dot v is simply 2. It's just the scalar, just the number 2. And this is the exact same thing if vector u and vector v had been written in the ij form. We would do the same process. We would get the exact same result. So that's it for the first quick example of how friendly it is to do dot product. Next we're going to see what dot product could be used for. Hey, next up we're going to look at an application of dot product. And here's a quick definition. If you have two non-zero vectors that I'm calling u and v, and theta is the angle that's between vectors u and v, then the cosine of theta, theta is the angle between the two vectors, cosine of theta will equal u dot v all over the magnitude of u times the magnitude of v. Let's do an example. Let's determine the angle, and now notice I'm saying in degrees, that's between vector u, which is 4, 0, and vector v, which is 2i plus 2j. So I thought in this example I'd give one vector in component form, the other vector in the ij form. Shouldn't matter. So here we go. I would first write down that the cosine of theta is u dot v over the magnitude of u times the magnitude of v. And now there's some things that I need to find here. In order to get the angle in degrees between these two vectors, notice what it's saying. I have to come up with u dot v. I have to come up with the magnitude of u. I have to come up with the magnitude of v. So let me kind of do that in this area here. Let's get u dot v. So u dot v, that's going to be a 4 times a 2. So 4 times 2 plus 0 times 2. That gives me 8. So the dot product of the two vectors is 8. I need to determine the magnitude of u. So magnitude of u. Well, that's the square root of 4 squared plus 0 squared. That's the square root of 16. 4. So the magnitude of u is 4. I need the magnitude of v. So magnitude of vector v. That's the square root of 2 squared plus 2 squared. And see, 2 squared is 4. 4 plus 4 is 8. Or if you prefer, that 8 would reduce down to 2 square root 2. So look, we have all the parts and pieces to substitute in here. We have cosine of theta is, well, u dot v is 8 over magnitude of u, we found the magnitude of u to be 4, times the magnitude of v. Magnitude of v is 2 square root 2. So we have cosine of theta, if I clean this up, 4 times 2 is 8, is 8 over 8 square root 2. Heck, if I clean it up some more, the 8's cancel out. So I have cosine theta is 1 over the square root of 2. And at this point you might be thinking, well, hey, we're trying to find an angle, so why don't we use our calculator and use angle finder, use inverse cosine. But I recognize this is something friendly off the unit circle. 1 over square root 2 is the same thing as square root 2 over 2. And if I know that point on the unit circle, I immediately know that theta is 45 degrees. So that's how we can use our knowledge of dot product to quickly get, or how to eventually determine the angle theta that's between two vectors. All right, here our final look here, dealing with dot products, and I kept up this little definition that I used in the last example, because the final topic deals with how do you determine if two vectors, two non-zero vectors, are orthogonal or if they're parallel. First off, we know what the word parallel means. Parallel means they would have the same direction. That's what two vectors, they'd have the same direction. Orthogonal is a very fancy word. It's a fancy word that's used when we're talking about vectors. But I just want you to remember orthogonal basically means perpendicular. You know, so two vectors would be orthogonal if they would, have a 90-degree angle. So here's two very quick definitions. Two non-zero vectors, u and v, are orthogonal, think perpendicular, if when you do the dot product of the two vectors you get 0. Look at why I know they would be orthogonal, why the angle between the two vectors would be 90 degrees if the dot product is 0. Look at what we just wrote down. Look what we have up here. Look what we used in the last example in finding the angle between two vectors. If my dot product is 0, the numerator of this fraction is 0. I don't care what the denominator ends up being, what positive number that denominator ends up being. 0 divided by any positive number is going to be 0. So cosine theta equals 0. That angle has to be 90 degrees. That's what would make that equation true. Second bullet item here. Two non-zero vectors u and v are parallel. Parallel. Same slope, same direction. If they are scalar multiples of each other. Or if u dot v divided by magnitude times magnitude of v equals plus or minus 1. So you can either think of it as two vectors are parallel if two vectors are parallel if they're scalar multiples of each other, or if when you do this stuff over here on the right, you take u dot v divided by magnitude of u, magnitude of v, you get 1 or you get negative 1. Now think about it. If this ends up being 1, this angle theta would have to be 0 degrees. If it's negative 1, it would be 180 degrees. Now think, if two vectors are parallel, if they're parallel, if you try to bring them together to have their initial points coincide, there's not going to be any angle between those two vectors. Let's do a quick example. Quick example. Typical example. You are asked, are the following vectors orthogonal, parallel, or neither? And the first one we'll look at here, two vectors are 2i, vector u is 2i minus 3j, and vector v is 6i plus a 4j. All right, so we're asked, are these two vectors, are they orthogonal? Remember, orthogonal just means perpendicular. Parallel means they're going in the same direction, or neither. Well, why don't we do this? Why don't we do the dot product? Dot product of u and v, that's 2 times 6. 2 times 6 plus negative 3 times 4. 2 times 6 is 12. Negative 3 times 4 is negative 12. 12 plus negative 12 is 0. So the dot product is 0. If my two vectors, if I do the dot product and I get 0, that tells me the two vectors are orthogonal. So these two vectors, they're that big fancy word, orthogonal, perpendicular. Let's do one more. Here, vector u is a negative 2i plus a 5j, and vector v is negative I plus a 5/2 j. Alright, so are these two vectors, are they orthogonal, parallel, or neither? Hey, here's the first thing that I notice. First thing I notice, if I take vector u, and I multiply it by 1/2. Well, look, if I take 1/2 times vector u, let's see what that would give me. That would be 1/2 times vector u. 1/2 times negative 2i plus a 5j. Well, if I distribute the 1/2, 1/2 times negative 2 is negative 1. 1/2 times 5 is 5/2. That's my vector v. So if I take 1/2 times vector u, I get vector v. So that's what I noticed. I noticed 1/2 times this vector gives me this vector. Vectors must be parallel. They're scalar multiples of each other. I took the scalar 1/2, multiplied it by u. So the scalar 1/2 times vector u gave me vector v. Vector v is a scalar multiple of vector u. So when that happens, my two vectors are parallel. Notice you could have also determined that they were parallel by doing a lot more work. You could do the dot product of these two vectors, which would be negative 2 times negative 1 plus 5 times 5/2. You could then find the magnitude of vector u, the magnitude of vector v, and you could do u dot v over the magnitude of u times the magnitude of v to see if you get a 1 or a negative 1. That would tell you that the vectors are parallel. I think this observation was a lot quicker and a lot more efficient. So that's it with a look at dot product and kind of a quick look at vectors in general, and hopefully this makes sense. Thanks for watching.